As I mentioned last time, we are going to spend this lecture on the review for the first exam. All right, so let me tell you what I would like to do in today's lecture. I will first give you the information and some important things about the upcoming exam, and then in the remaining lecture, I'm going to, show you one example of every single topic that we have seen from the beginning of the course until the last lecture. All right. So plan is to, discuss. We will not get into theory behind every single topic. Instead, I will try to remind you the general idea, step by step idea to, handle particular type of examples. All right. So starting with the information about the exam, as you know, the first exam is scheduled on Monday, March 1st. It will start at 7 p.m. ends at 8:45 p.m. All right. So starting at 7 p.m. on Monday, you should be able to access exam one folder. You will have to download the exam, and then you will have to fill out your information, and you will have to write the solution by 8:45 p.m. Now, once the exam is done, we will give you about 30 minutes to scan and upload your work. All right. So from 8:45 p.m. to 9:15 p.m., you can scan and upload your work. If you don't have a printer, then you can write down the solution of your exam question on a separate piece of paper. As I mentioned earlier, it is preferred that you write one question solution per page. All right. So try to neatly organize your work if you are writing on a separate piece of paper. Yes, it is absolutely fine to write your exam digitally if you are using your iPad or a tab to write down the solution of the problem. That will be perfectly fine. And if you have any special accommodation, yes, you will get that accommodation. All right. Um, There is a penalty for the late submission. You will notice that at 8:15 p.m. the exam uploading link will disappear. All right, and new link will pop up, and this new link will say late exam submission. This link will remain open until 9:45 p.m. And as I said, the penalty will be 1 point penalty per minute late submission. Those of you who know the content very well, trust me, you should be able to finish the exam in about 1 hour or so. All right. Um, if you finish early, feel free to upload your work early. It should be perfectly fine, right? But after 9:15 p.m., as I said, penalty will be applied for late submission. All right. Late submission link will remain open until 9:45 p.m. So maximum penalty that you can receive is 30 points on the exam. And if you fail to submit your work by 9:45, then you will have to email me with your work, right? And that means 30 minutes penalty plus whatever time it will take. So again, if there is any issue in uploading and scanning the exam, you should send me an email um, during that time period. All right, and I will be more than happy to help you out. Okay. Now let me talk a little bit about the exam itself. I'm planning to give you 8 questions on the first exam. All right, so total number of questions will be 8. Of course, each question will have some sub problems, right? So some question will have part A, B, and C, or A and B, or some question they are just one question by itself. All right. Let me tell you how we want you to upload your work. All right. You will notice when you go to exam folder, you will notice 9 different links. In the first link, I want you to upload the cover page information only. All right, the first page information. If you don't have a printer, write down your name, UTD ID, your lecture section number on the first page, and then upload, scan and upload that first page in the first link. All right. The remaining 8 links are for each question. All right. So first link, you will be uploading first question solution. In the second link, you will be uploading second question solution, and so on and so forth. Right. So uploading question in particular link will help grader, and it will help you know you guys too to see how the things are graded. We are going to do grading uniform, so one person will be assigned to grade one problem for all the students who are taking this course. All right, so for uniformity purpose, we are making this particular arrangement of uploading one question per link. All right, and if there is any issue, just let me know. Most of you already know that when you upload a document on e-learning, e-learning immediately send you confirmation email on your UTD email ID saying that your document has been uploaded. Once you upload it, I want you to double check that link and verify that your upload did go through. If it doesn't go through, just send me an email and I will help you out there. Okay, so these are the um, main steps that I wanted to discuss before your first exam. If you notice, I have posted a PDF file on the exam section. I also have sent an email announcement to all of you regarding details of the first exam. I want you guys to read all those instructions carefully, and if there are any questions, just let me know and send me an email, and I will be happy to help you out there. Okay. All right, so this is the information about the first exam. Now let's get into this review part. If you remember, from the beginning of the semester until the last lecture, these are the list of topics we have covered so far. We talked about basic operations on polynomial. We learned how to add, subtract, multiply, and divide two polynomials, right? Division of two polynomials requires concept of factorization. So we talked about factorization carefully. We handle division of two or more polynomial in terms of rational expression. And then we turn over to the equations, right? So we talked about linear equation, quadratic equation, and rational equations. We also talked about exponents and radicals, right? And then we learn how to solve the exponential equations. We talked about function. For function, we learn how to calculate its domain, how to calculate intercepts, and how to calculate asymptotes, right? We talked about two interesting functions, namely logarithmic function and exponential function. We realized that log is the greatest simplifier in mathematics, right? And we have seen how to use logarithmic rules to expand a single complicated log into multi-term expression or multi-term expression into single complicated single logarithmic expression, right? So we know both ways to expand a single term expression into multi-term or to condense multiple terms into a single term, right? And then if you remember, lately we have been talking about the idea of calculus, right? We talked about limit of the function, and in the last lecture, we also learned how to compute limit at infinity and how to determine continuity of the function. Now, let me start this review with the first topic. And as I said, our goal is very clear. I'm going to give you one problem of each topic. I'll remind you the logic behind the solution. And if you have any question with that, feel free to, turn on your mic and ask that question. Okay. All right. So let's start this review by recalling um, the basic operations on polynomials. we know how to add, subtract, and multiply polynomials. And I would like to start this discussion by showing you few examples, right? So let's say perform the given operations, right? Let's say I would like to subtract two polynomials. Suppose I give you 2 times 3x squared plus 4x minus 5 minus 3 times 2x squared minus x plus 7. All right. Fairly simple. How to subtract two polynomial. What I would like to do is I would like to distribute this 2 over every single term in the first parenthesis, and I would like to distribute -3 over every single term in the second parenthesis. Right, and then I would like to deal with the like terms. Let's do that. I really get 6x squared plus 8x minus 10 minus 6x squared plus 3x minus 21. Looks like we have 3 sets of like terms here. I want you to simplify them. Look, 6x squared minus 6x squared, that's 0x squared. 8x plus 3x, that's 11x. And then -10 minus 21, that's -31. And that's pretty much it, right? So we can perform addition and subtraction of 2 or more polynomials. We can even multiply 2 or more polynomials. Let me show you a couple of examples. Suppose we would like to multiply 3x plus 4 with 4x plus 5, right? We can use two methods to do this. You can use the FOIL method if you like, or you can use the distribution method, right? Distribute the first factor over every single term in the second parenthesis, or use the FOIL method. Let me use the FOIL method here. I'm going to show you one more problem that uses that distribution idea. I'm going to multiply 3x with both of this term. I'm going to multiply 4 with both of this term. And then I will take care of the like terms. Let's do that. Look, 3x times 4x is 12x squared. 3x times 5 is 15x. 4 times 4x is 16x. And 4 times 5 is 20. I'm going to simplify these like terms. I get 12x squared plus 31x plus 20. And that is my final answer, right? As I said, we can even consider this type of example: 2x plus 3 times x plus x squared plus 3x minus 4. As I said, our goal remains the same. I'm going to distribute this factor over the first term, over the second term, over the third term. Or you can use the method similar to the FOIL method. The reason why I'm saying that is because I already did it here in the first example. Look, I distributed 2 over all these 3 terms. So imagine that this is the entry similar to 2, right? Do exactly the same thing that you did here with 2. I distribute that 2x plus 3 to x squared to the second term 3x. So 3x will also get a copy of 2x plus 3. And then that -4 will also get copy of 2x plus 3. So I distributed 2x plus 3 over all 3 terms. Now it's time to distribute that x squared over both terms, 3x over both terms, and -4 over both terms. Let's do that. I get 2x cubed plus 3x squared plus 6x squared plus 9x minus 8x minus 12. Take care of like terms and you are done. We get 2x cubed plus 9x squared plus x minus 12. All right. And that's how we multiply two polynomials. Now remember, division of two polynomials require the concept of factorization. So after learning these operations, we turn our attention towards factorization techniques. Factorization must be handled in three stages, right? Stage one, look for the greatest common factor. If there is something common between the given terms, you will have to pull it out. Stage two is really the factorization idea to factorize trinomial of the form ax squared plus bx plus c. We also know how to factorize them, right? And then stage three is a spatial factorization formula where we have formula to factorize difference of two squares, sum of two cubes, and difference of two cubes, right? And as I mentioned, we have to use this formula, we have to use this strategy in the appropriate order, in this exact order, all right? Let me show you a couple of examples that, mix and match two stages out of these three, all right? So here are two simple examples. Let's say factorize the given polynomials. So here is the first example. Let's say we would like to factorize x cubed minus x squared minus 20x. All right. Notice that there are three terms in here. All right. I'm going to look for the common factor first. Looks like the common factor between these three terms is x. I'm going to pull x out. All right. Let's write down what's left over from each of these terms. X squared is left over from the first term. X is left over from the second. Minus 20 is left over from the third term. I want you to notice that bracket inside expression is a trinomial of the form ax squared plus bx plus c. The question is, can we factorize it further? Let's check. I'm looking for the factors of negative 20 whose sum is negative 1. Are we aware of any such factors? Answer should be yes. Negative 5 and positive 4. These are the two factors whose product is negative 20 and their sum is negative 1. The next question is, can I write down the factorization directly? Well, this is a monic polynomial. Coefficient of x squared term is 1. I can write down the factorization directly. The factorization of this trinomial will be x minus 5, x plus 4. And this is the complete factorization of the given polynomial. Once again, it's a simple idea. There is no trick. I will also show you an example where we don't have a monic polynomial, just to recall the actual process. Okay. So, but for now, convince yourself that one can create a problem that involves two factorization stages out of three. Here is one more before we move further. Here is the second one. Let's say I would like to factorize 2x cubed minus 50x. All right. Once again, the idea remains the same. There are two terms. I'm going to look for the greatest common factor, which is 2x. 2 is the common factor between number. 1 power of x is the common factor between power of x. Inside the parenthesis, we are left with x squared minus 25. All right. Notice that this is not a trinomial. All right. So I cannot use this method. The question is, can we factorize it further? We only have one more idea left, and that goes through spatial factorization formula. Think about it. Can we visualize these two terms as a difference of two squares or difference of two cubes? Looks like square root of each of this term is a clean entry. So we can visualize this as a difference of two squares. I can certainly write this as, x square minus 5 square. So this is in the form of a square minus b square. The factorization would be a minus b, a plus b, and that is full factorization of the given polynomial. So now we also have idea about factorization. We can now talk about division of two polynomials. Let's talk about it. As I said, would like to give you few examples of how we handle division of two or more polynomials. So the first one is kind of simple. Let's say I would like to simplify the following expressions. Say I give you these expressions: x square plus 2x divided by x square minus 4, and this is divided by let's say we have x square plus 3x over x square minus x minus plus x minus 6. All right, let's try this one out. Let's see what happens. Okay, my goal is very clear. I wanted to factorize every single polynomial in the top and the bottom. I wanted to cross out the repeating factors, and I wanted to simplify it. Let's do that. Okay, first of all, change that division sign into multiplication sign carefully. So I get x square plus 2x over x square minus 4 multiplied by x square plus x minus 6 in the top, and then x square plus 3x will be in the bottom. Okay, let's factor everything out. I'm factoring x out from these two terms. I get x plus 2 in the parenthesis. Factoring x square minus 4 gives me x minus 2, x plus 2. Likewise, factors of negative 6 that adds up to 1, it's going to be x minus 3x plus 2 because this is a monic polynomial. And factor 3 out, you get factor x out, you get x plus 3 in the parenthesis. Right? Oops. X plus 3x minus 2. Factors of negative 6 that adds up to 1 are going to be positive 3 and negative 2. Yeah? All right. Time to get rid of the repeating factors. All right. So looks like x is gone. X plus 2 is gone. X minus 2 is gone. X plus 3 is gone. Left over is really 1, right? This whole thing simplifies to 1. Once again, the idea should be clear. We would like to factorize every single polynomial in the top and the bottom, and then we would like to get rid of the repeating factors to simplify it. All right. There is no guarantee that everything will cross out. This is nicely designed example, and that's why everything is being eliminated. But you may get some expression involving x in the top and the bottom as your final answer, which is absolutely fine. Okay. All right. Now, after this, we learn how to solve the equation. Remember, difference between equation and expressions needs to be clear in your mind. Expressions can be simplified only. Equations can be solved for the given variable. Let's try to recall this idea. There are 3 types of equations we have discussed, right? Linear equation, quadratic equation, and rational equations. Solve the following equations for the given variable. Here is the first example. Let's say I give you this equation, 2 times 3p minus 4 plus 5 equal to 3 times p plus 1 minus 7. All right. Um, all I have to do is simplify both sides as much as possible. Get 6p minus 8 plus 5 equal to 3p plus 3 minus 7. Let's take care of like terms from both sides. Negative 8 plus 5 is negative 3, and then 3 minus 7 is negative 4. All right. Now think about it, how to solve this for variable p? Well, in order to solve it for variable p, I need to isolate term containing p. I need to isolate the like terms using equality. So I'm going to send this 3p over to the left side. At the same time, I'm going to send that negative 3 to the right side. So add negative 3p on both sides, add 3 on both sides. Now remember, this is really intentional move, right? There is no need to write 3p minus 3p on the left side to cross 3p out. This was intentional. It's perfectly fine to skip that step. 3p, 6p minus 3p adds up to 3p, and then negative 4 plus 3, that's going to be negative 1, right? Okay, solve this for p, divide both sides by 3, and we are done. This is really the solution of the given linear equation. All right, we also learned how to solve a quadratic equation. So let me show you one example. So let's say we have this equation that we would like to solve for the variable x. 3 times x squared plus 1 equal to 2 times x minus 1 plus 10. All right. We would like to solve this equation for variable x. It's an example of a quadratic equation. Let's carefully simplify both expressions. I'm going to distribute 3 over both terms. So I get 3x squared plus 3. I'll distribute 2 over both terms. So 2x minus 2 plus 10. All right. Simplify those numbers. I get 2x plus 8. On this side, we have 3x squared plus 3. Let's shift everything to the left side, right? Add negative 2x on both sides and add negative 8 on both sides. Let's take care of those two like terms. See what I get, 3x squared minus 2x minus 5. I get this quadratic equation. I would like to solve this for variable x. Let's solve it. This is what I need to do. Find the factors of negative 15 whose sum is negative 2. Find the factors of negative 15 whose sum is negative 2. Looks like negative 5 and 3. These are the two factors that adds up to negative 2. The question that we have is, can I write down the factorization directly? Answer is no, because this polynomial is not a monic polynomial. All right. So we have to go through that three-line argument. Break the middle term into two pieces. That negative 2x, I'm going to write it as negative 5x plus 3x. Let's do that. Negative 5x plus 3x. That's how I break that middle term. So we are rewriting middle term based on those two pieces. Group the first two terms, group the last two terms, and take the common factor out. Common factor between first two terms is x. Common factor between the last two terms, there is nothing common, so 1. All right. So as I said, this gives you an opportunity to convert 4-term expression into 2-term expression. Now, take out the common factor between these two terms. 3x minus 5 is the common factor. Pull it out. This is what I get. Product of two factors becomes 0 if one of them itself is 0. So all I need to do now is set 3x minus 5 equal to 0 and x plus 1 equal to 0 and solve for x. This is a linear equation. Add 5 on both sides, divide both sides by 3. Add -1 on both sides, and you get the solution of your quadratic equation. Once again, it's not a difficult thing, as I said. I really wanted to recall the idea of how to, show a complete work for trinomial of the form ax square plus bx plus c, where a is different than 1. All right, and that's the reason why we formulated example in this particular way. Okay, now let's move on and let's talk about how to solve rational equation. All right, if you remember in the lecture, I showed you two examples. In first example, we had two legitimate solutions of the given rational equation. In the second example, we had two solutions, but they both were the fake solution. And I mentioned that on your paper homework assignment, we put one question where you have one fake solution and one good solution. All right. I would like to show you in today's lecture the example where we have one good solution and one fake solution. So let's try this problem. Let's say we have, this is the third problem where we would like to solve quadratic equation x over x plus 2 plus minus 2 over x equal to 4 over x times 4 over x squared plus 2x. All right, let's work with this particular example. Okay, so I already mentioned this earlier that there are many different ways to handle rational equation. Out of them, this will be the simplest way. Find the common denominator of all the terms and multiply every single term by that common denominator. Think about it. What does that do? That will help you eliminate denominator completely from your example. And this is the reason why I say this is the simplest and fastest way to handle rational equation. Let me find out the common denominator of all the terms. I have x over x plus 2 minus 2 over x. On the other side, I have 4 divided by x times x plus 2. I factorize every single entry in the denominator. Now find out what is the common denominator. Looks like the common denominator of this 3 term is going to be product of x and x plus 2. What I'm saying is if you multiply every single term by x times x plus 2, that will eliminate denominator completely from our example. Let's do that. I am multiplying first term by x times x plus 2, second term by x times x plus 2, and the one on the other side by x times x plus 2. All right. So I multiplied every single term by x times x plus 2. Now, as I say, this will help me eliminate denominator completely. Look at the first term. X plus 2 is gone. X is gone. X is gone. X plus 2 is gone. Now, be very, very careful. When you cancel expression involving variable, you need to mention Whatever you are cancelling is different than 0. All right, so this really requires the condition x plus 2 cannot be 0, meaning x cannot be 2. To cross out this x, you need condition that x cannot be 0. So these are the two conditions that are needed in order to get rid of those denominators. Let's write down what's left over, right? X times x is x squared. Then I have minus 2 times x plus 2. On the other side, I have 4 that survives, right? Notice that the denominators are gone completely, right? But this condition is required to go from here to here, okay? All right, looks like that's a quadratic equation. We know how to solve it. We just solved one quadratic equation recently. Let's solve this one too. Add -4 on both sides to shift that 4 from the right side to the left side. I get x squared minus 2x minus 8 equal to 0. Do we know any factors of -8 that adds up to -2? Answer should be yes. -4 and +2, right? I can write down this factorization directly. Look, x minus 4, x plus 2 equal to 0. I'm setting each of this factor equal to 0 to solve for x. Looks like I get x equal to 4 and x equal to -2. Now, this is how I want you to interpret this solution. X equal to 4 and x equal to -2, for sure, they are the solution of your quadratic equation. The question we have is this: are they the solution of this rational equation too? Well, to answer that question, you will have to go through the validation of your solution. All right? To go from rational form to non-rational form, I need this restriction. X cannot be 2, x cannot be 0. All right? Looks like I get x equal to -2 as one of the solution, right? Since that was a necessary condition to go from rational form to non-rational form, I cannot accept this as a solution. I would simply say this is not possible. It's a fake solution, in other words. X equal to 4 doesn't coincide with any of the restriction that we have. So this is the legitimate solution. So this is one problem where you have one fake solution, one good solution. All right. So keep this example in mind. Very interesting problem. All right. Now, if you remember, after that we talked about exponents and radicals. Let me remind you this idea quickly with a couple of examples. So first example that I would like to discuss is simplification of rational expressions involving radicals and exponents. So let's recall the idea. So here is the example. Let's say simplify this expression. We have 3x squared square root of y over z cube to the power 2 multiplied by 2x times cube root of z over y to the power 4, entire thing to the -3. All right. Suppose we would like to simplify this rational expressions involving exponents and radicals. Remember, I gave you the general step-by-step idea to handle this situation. Let me remind you those steps. Step 1 is to convert outer negative exponent into positive exponent. So if there is any outer negative exponent, I would like to turn it into positive exponent by simply switching the top and the bottom of the base. All right. Once that is done, I will distribute outer exponent to every single factor of the base. All right. Simplify numbers and then multiply power of powers. And then shift everything in the numerator and simplify the exponents. All right. So that's all we are going to do in this example. Let's do it. I'm going to first remove those fancy notation and write them as a numerical power. So look, I get 3x squared y to the 1 by 2 over z cube to the power 2. And this is multiplied by, let me change that negative 3 to positive 3. So this denominator will go in the top and top will be going into the denominator. Again, I'm rewriting that cube root of z as 1/3 power of z. Okay? All right. Time to distribute that outer power to every single factor of the base. Look, there are 4 factors here for the base. Each of this factor will get that 2 power. So 3 will get 2 power, x square will get 2 power, y to the 1 by 2 will get 2 power. Okay, let's change this 3 to 4. Okay, I really would like to show you something where we need to deal with the fractions. Okay, with that 2 and 3 power, the fraction will be eliminated, right? So let's try to change that negative 3 by negative 4. Okay, I get that z cube will also get 2 power. Same way, each of this factor will get 4 power. Y to the 4 is getting 4 power. 2 is getting 4 power. X will get 4 power. And z to the 1/3 will get 4 power as well. Okay. As I said, simplify numbers and then multiply power of power. 3 square is 9. So 9 will be in the top. 2 to the 4 is 16. 16 will be in the bottom. And now I'm going to multiply the power of power. X square, that's x to the 4. Y to the 1 by 2 times 2. 1 by 2 times 2 is just 1. So this is y to the 1. Z to the 3 times 2. So this is z to the 6. And then I have y to the 4 times 4, which is 16. X to the 4. And then z to the power 1/3 times 4 is 4/3. All right. Okay. Final step. Move everything in the numerator and then simplify the exponent sharing the same base. So 9 over 16 will stay in the front. X to the 4, y to the 1, y to the 16, z to the negative 6, x to the negative 4, and z to the negative 4/3. That's gonna stay in the numerator. Okay, if 2 exponents sharing the same base, they are multiplied together, then you can add the powers. Let's do that. 9 over 16, x to the power 4 minus 4. All right, x to the power 4 minus 4 is what I get. 4 plus negative 4. Y to the power 1 plus 16, and then z to the power negative 4 by 3 minus 6. We know how to handle the fractions, right? All you have to do is find the common denominator, make it visible under both terms, and then simplify the numerator, right? So negative 4 minus 18, that's negative 22 over 3. I'm gonna do that over here. Let's do that. 9 over 16, x to the power 0, y to the 17, and z to the negative 4 by 3 minus 18 by 3. Okay. All right. What is the zero power of any variable? Zero power of any base is going to be 1, right? So this is 1. Replace it by 1. I get y to the 17 here and z to the negative 22 over 3. Okay. All right. If nothing is said, you can stop right there. This is our final answer. If the question says, write your answer with all positive exponents, then you have to send that into the denominator. You have to basically write one more step, 9y to the 17 over 16, z to the 22 over 3. All right. So again, if instruction says, write your final answer with all positive exponent, this is where you need to stop. Okay. So this is how we solve expression involving radicals and exponents. Turn outer negative exponent into positive exponent, distribute outer exponent to every single factor of the base, simplify numbers, multiply power of powers at the same time, shift everything in the numerator, and then simplify the powers sharing the same base. All right. Okay. We also talked about rationalization. Let's try to recall this rationalization process with one quick example. So let's say I would like to simplify this expression, 12 divided by 3 minus square root of 7 plus 5 square root of 7. All right, so understand that our intention is very clear. There is only one term that has radical in the denominator. All right, this term does not have radical in the denominator. All right, so my goal is clear. I'm going to rationalize this first term, and then I will replace this term by its rationalized version, and I will simplify the like terms. All right, so we are going to do this solution in 2 steps. Step 1, simplify, rationalize this first term by itself, and whatever the rationalization is, use it as a replacement of your first term, and then simplify the like terms. So here is the solution. So as I said, I would consider the first term only, 12 over 3 minus square root 7. As I said, my goal is to get rid of the radical sign from the denominator. To do that, I'm going to multiply and divide this by a conjugate of the denominator. The conjugate of the denominator will be 3 plus square root 7, right? Look, the formula is complete in the bottom. A minus b, a plus b. I can write this in form of a square minus b square. So 3 square minus square root 7 square. All right. 3 square is 9. Square root 7 square is 7. And 9 minus 7 is just 2, right? So 12 times 3 plus square root 7 over 2. We can cross out 2 as a factor from top and the bottom. That gives me 6 times 3 plus square root 7. What I'm saying is we have 2 ways to write this expression. Either you write it in this form where you have radicals in the denominator, or you can write it in this form where the denominator is clean. Denominator does not have radical, right? The idea is pretty clear now. If you want to simplify, so now, if you want to simplify 12 over 3 minus square root 7 plus 5 square root 7, all you have to do is following. Replace this by its rationalization. 6 times 3 plus root 7 plus 5 root 7. I'm gonna distribute that 6 over both terms. Look, I have two like terms here. 6 square root 7 plus 5 square root 7. Add them. How you add 6x and 5x? 11 square root 7 is what I get. Right? So 18 plus 11 square root 7. This is how you can write down that sum. That sum itself looks ugly, but this one looks pretty nice, right? So rationalization, do this this interesting thing to reduce that complicated expression into something very nice. In the last lecture, you guys have seen how rationalization can be used to handle indeterminate form of the limit, right? So this is the reason why we were interested in this whole idea. Now, if you remember, after this we turn our attention onto the concept of function, right? For function, we learn how to calculate its domain, how to calculate its range, how to calculate intercepts, vertical and horizontal asymptotes, and how to identify a hole in the function, right? Let's try to recall that idea with one quick example, all right? So here is an interesting problem related to functions. Let's say I give you this function for f of x equal to x squared plus x minus 6 divided by x squared minus 4. Suppose I give you this rational function. All right. We would like to ask a series of questions about this function. Question number 1, give the domain of the function. Compute the domain of this function. Question number 2, give x-intercept. Now let me make it very clear that when I say x-intercept, this is a word that is being used for the point on the graph of the function. When I say graph of the function, every single point will have two components, x component and y component, right? So x-intercept will be in the form x comma y. Compute y-intercept. All right. Then calculate vertical asymptotes. Calculate horizontal asymptote. And then final question would be, does f of x, or does the graph of f of x have a hole? If yes, give the x value where hole occurs. All right. Let's try to answer all these questions carefully. And perhaps by now you should be able to relate many of this concept with the theory of limit. And I'll make a note about that. But for now, let's work with this function. Remember, our first goal is to identify if this function has a hole or not. Since it's a rational function, we would like to convert it into proper rational form. We would like to make sure that, there is no cancellation in the top and the bottom. If there is a cancellation, we would like to perform it. Look, factors of negative 6 that adds up to positive 1 are going to be x plus 3, x minus 2. Factors of x squared minus 4 is going to be x minus 2, x plus 2. I want you to notice the cancellation of x minus 2. All right. Let's write down this function in a simpler form. X plus 3 over x plus 2. Remember, I am crossing out expression involving variables from the denominator. So I need to top and the bottom. So I need to say that whatever I am cancelling is different than 2. All right. Let me tell you how to interpret these two expressions. I am saying this, that these two functions, they are exactly the same except at input 2. All right. Again, these two functions are exactly the same except for x equal to 2. What's different in x equal to 2? At x equal to 2, this function has a hole. At x equal to 2, this function does not have a hole. If you draw these two functions in your calculator, you will realize that this function will have a hole at input x equal to 2. This one does not have a hole, right? So that's why we are saying that this can be simplified to that under that restriction that x is different than 2. Remember, the factor that you are crossing out, it represents the location of the hole in the graph of your function, right? As I said, I am going to use that reduced version to get answer to these 4 questions. I'm going to calculate the intercept and vertical horizontal asymptotes using that reduced version of the function. Okay, let's try to do this computation. What is the domain of this function? We already identified 2 as a bad input. There is a hole in the function, so 2 is a bad input. What else is a bad input? Negative 2. You can compute domain by setting this equal to 0 as well. You will get the same thing. Remember, if you are using this entry, then take into account that additional restriction as well. Negative infinity to negative 2 union negative 2 to 2 union 2 to infinity. That is the domain of this function. How do we find x-intercept? By setting y equal to 0. So set y equal to 0 and solve for x. Look, I'm setting 0 equal to x plus 3 over x plus 2. Multiply both sides by x plus 2 to eliminate the denominator and then solve for x. I get x equal to negative 3. What is the x-intercept? Well, x-intercept is the point where x value is negative 3, y value is 0. So this is your x-intercept. Remember, if you don't write your answer in form of x comma y format for the intercept, you will lose some points. Okay, so x-intercept, it is a point of the form x comma y. How do we calculate y-intercept? Set x equal to 0 in your function. I'm going to use that reduced version as I said. I'm setting x equal to 0. Looks like I get y equal to 3 by 2 right away. What is the y-intercept? It occurs when x is 0 and y is 3 by 2. All right. Okay, how do we calculate vertical asymptote? There are 2 bad inputs for this function, 2 and negative 2. 2 has been identified as a hole. Negative 2 is vertical asymptote. For vertical asymptote, you will have to find the 0 of the denominator of that simplified form. So the line x equal to negative 2 is a vertical asymptote. All right. What's the horizontal asymptote? Remember how to calculate horizontal asymptote? Write top and the bottom polynomial in form of equal degree polynomials, right? And once they are in form of equal degree polynomial, take the ratio of the leading coefficients. These both are in form of ratio of equal degree polynomial. Degree of top polynomial is 1, degree of bottom polynomial is 1. So the ratio is going to be 1 over 1 or y equal to 1. This line represents horizontal asymptote for our function. The function, of course, have a hole, all right, and the location of the hole, we already know that x equal to 2 is where the hole occurs for the graph of our function. Now let's try to see connection of this question with the concept of limit. All right, look, limit 0 means it's an x-intercept. All right, look, if I ask you what is the limit of this function when x approaches to -3, limit of this function as x approaches to -3 is going to be 0. X-intercept really represent the limit equal to 0 case. All right. Okay. What does vertical asymptote represent? Vertical asymptote represent the case when the limit does not exist for your function. Think about it. What is the limit of this function as x approaches to -2? It gives you 0 in the denominator, meaning that vertical asymptote really is linked to, the case where the limit does not exist for your function. What does horizontal asymptote represent? Remember the idea of limit at infinity? Limit at infinity, that is really related to the horizontal asymptote. Look, this is the polynomial of equal degree. What is the limit x goes to infinity of ratio of these two polynomial? Well, it's going to be ratio of the leading coefficient. So horizontal asymptote does represent limit at infinity for the given function. All right. And then last but not the least, whole. A whole really represent indeterminate form of your function. If I ask you what is the limit of this function when x approaches to 2, if you plug x equal to 2 in here, you get 0 over 0 form. After factorization, if you cross out 2 and if you plug your limit in here, you will get the value. All right. So again, understand how to relate all these things with the concept of limit. Okay. Now let's move on and let's talk about exponential equation and logarithmic rules. And once we have that, we will go over the concept of limit and continuity, depending on how much time we will have. So let me show you examples here for exponential equation. Let's say solve the following equation for variable x. Here is number 1. Let's say we would like to solve 2 to the x square over 64 equal to 32 to the x. And here is the second example. Let's say we have 3 to the 2x plus 1 times 2x minus 1 equal to 3 to the 2x plus 3. All right. The first problem, it's a straightforward problem. We did series of problems like this in the class. The idea is this. I noticed that x is in the exponent. All right. So the variable is in the power of some base. The only way to deal with this is, if possible, express both sides in form of exponent sharing the same base. What it means is that I want you to write down each of this term in form of exponent with base 2. Let's do that. 64, we know that it's 2 to the power 6. 32 is 2 to the power 5. So again, my goal is very clear. I want to write both sides in form of exponent sharing the base 2. What is the advantage of this? If two exponents sharing the same base are equal, then the power should match. When I equate the power, I'm going to get, either a quadratic or a linear equation that can be solved easily. All right, let's try. Um, we do power of power gets multiplied, so the right side becomes 2 to the 5x, and then here I have two exponents sharing the same base and they are divided by each other, so I'll have to subtract the powers. All right, now look, I express both sides in form of exponent sharing the base 2. This is only possible when the powers are equal. So you set their powers equal. All right, what is that? That's a quadratic equation. Solve it. Add negative 5x on both sides. Factors of negative 6 that adds up to negative 5 are going to be negative 6 and positive 1. If you set each of these factor equal to 0 and solve for x, you will get x equal to 6 or x equal to negative 1. So these are the two solutions of given exponential equation. All right, now let's look at the second example. Why second example is more interesting than the first one? The first example had variable x in the power only. The second example has variable x in the power as well as polynomial involving variable x is being multiplied by exponential term. This is what makes the idea more complicated. This looks more tedious because variable x is down there as well. The question is there any way that we can get rid of variable x from the power? Look, here we had a way. We represented both sides in form of exponent with base 2, and then we equated the powers. This is how we got rid of that base 2. Can we do something similar? Well, because that x is down there, looks like that door is shut. So what I do here is I notice that 3 has power 2x here, 3 has power 2x here on the other side too. So the best that I can do here is to separate, this 2 powers of 3 on the left side and 2 powers of 3 on the right side, right? I can write down 3 to the 2x plus 1 as 3 to the 2x times 3 to the 1. 3 to the 2x times 3 to the 3, right? So I'm breaking it down. Notice 3 to the 2x appears as a factor on both sides. Dividing both sides by 3 to the 2x will eliminate exponential term from your example. So technically this problem is simpler than the first one. This is a linear equation. Divide both sides by 3. Add 1 to both sides. Divide both sides by 2. You get the solution of your equation. So as I said, there is no trick here. You need to be sure which strategy to use, which type of example. All right. Let's move on and let's talk about logarithmic rules. I just would like to show you one quick example. So let's say I give you this problem, expand the following expression. Suppose I give you a function in form of, let's say, log of 2x cubed square root of 2x plus 3 e to the x plus 5 times 2x plus 1 cube. All right. Obviously, in order to expand this, I will have to calculate number of distinct factors inside that log. To calculate such factors, first step is to write each term in its proper form. Right? By proper form, I really means if there is a square root or cube root sign, I want you to, write them as a numerical power. Now count how many factors do I have in the top and the bottom. Look, there are 1, 2, and 3 distinct factors in the top, 1 and 2 distinct factors in the bottom. Altogether, I have 5 distinct factors inside that complicated log. What does this mean? This means I can break this log into exactly 5 pieces. Let's break it down. Look, this is what I get. Log 2 plus log x cubed plus log 2x plus 3 to the 1 by 2. The factors sitting in the top will have positive sign in between. The one in the bottom will show up with the negative sign, right? So log e to the x plus 5 minus log 2x plus 1 to the power 3. Now it's time to shift the powers in the front. Shift all these powers in the front. All right. I get log 2 plus 3 log x plus half log 2x plus 3 minus x plus 5 times log e. Remember, log e is 1. 3 2x plus 1. All right. This is how far you can expand it. And as I said, log e is 1. So you can, remove that. And this is going to be our final answer. This is how we can expand single term logarithmic expression into multi-term expression. All right. Now, let's try to recall the idea of limit and continuity briefly with few examples. If you remember, in the last lecture, I gave you series of examples to handle the limit. I'm going to, remind you a few more examples here. All right, evaluate the following limits. Here is the first example. Let's say I would like to calculate limit x approaching to 2 of 2x squared plus 1 over x plus 5. All right, what's the best way to understand behavior of this function when x is near to? You would say plug x equal to 2 into the function and see what happens. So I'm going to plug x equal to 2 in here. 2 times 2 squared plus 1 over 2 plus 5. Looks like I get 8 plus 1 in the top, 7 in the bottom, 9 over 7. I end up with the number, and this number is the limit of the function. All right. Same way, if I ask you to compute limit x approaching to 3 of 2x minus 6 over x plus 1, look what we get. 2 times 3 minus 6 over 3 plus 1. I get 6 minus 6 in the top with 4 in the bottom. Looks like the limit is 0. How to read this in terms of the graph of the function? This is how I read it. This function has x-intercept at x equal to 3. Again, this function 2x minus 6 over x plus 1 has x-intercept at x equal to 3. That's how I read that limit statement. Let's try one more. Suppose I ask you to calculate limit x approaches to 5 of 2x plus 1 over x square minus 25. Plug x equal to 5 and see what happens. Looks like we get 11 in the top with 0 in the bottom, meaning limit does not exist. How do we read this question in terms of graph of the function? Well, this function has vertical asymptote at x equal to 5. That's another way to read the same statement. Now, these are 3 base cases, as you know, and we have some, another interesting situation. What if you get 0 in the top and 0 in the bottom when you plug x equal to a into your function? If this is the case, then you call it indeterminate form of the limit. Let's say we would like to calculate limit x approaching to 3 of x square plus x square minus 2x minus 3 over x square minus 9. If you plug x equal to 3 into your function, you will realize you get 9 minus 6 minus 3. So this is 9 minus 9. in the numerator. Let's actually write this down quickly. All right, so I get 9 minus 9 in the top, 9 minus 9 in the bottom. This is an indeterminate form of the limit. All right, so this simply means that direct substitution, like in the previous three cases, it worked, but in this case, it did not work, right? What do I do here? Well, use factorization, rationalization, or algebraic simplification. Clearly, I need to use, factorization here because I have a ratio of two polynomials. Factors of -3 that adds up to -2, x minus 3, x plus 1. Factors of x square minus 9, x minus 3, x plus 3. Look, I cross out x minus 3 from top and the bottom. This should look familiar to you. This should look familiar to you. We are crossing out the whole from the top and the bottom. All right. Now apply the limit on the remaining part of your function. Now remember, limit is a prediction only. We are making prediction that when x goes close to 3, your function will go close to 2 by 3. All right. Exact value of your function at 3 may or may not be same as 2 by 3. All right, so be sure about this thing. Let me show you one more example of indeterminate form where we use, rationalization technique. Perhaps something like this. Let's say I have limit x approaching to 1 of x square minus 1 over square root x minus 1. It is crystal clear that if you plug x equal to 1, you get 1 minus 1 in the top, 1 minus 1 in the bottom. This is indeed 0 over 0 form. I would like to, make the problematic portion visible using factorization, rationalization, or algebraic simplification. This is a polynomial, so factorization is what I need to use for the top expression. This is a radical expression, so rationalization is what I need to use there. If you factorize top, you get x minus 1, x plus 1. If you rationalize the bottom, you will have to multiply and divide your expression by square root of x plus 1. Look, a minus b, a plus b is complete in the bottom. You can write it as a square minus b square. All right, so a square minus b square, square root x square is just x, minus 1 square is 1. Look at that, problematic portion is gone. You can now apply the limit on the remaining part of your function. Looks like if you replace x by 1, you get 1 plus 1 in the first bracket, 1 plus 1 in the second bracket. The limit is going to be 4. All right. Okay, looks like we are running out of time, but since we only have about 2 more topics left, let me at least show you an example of each of this topic. Won't take more than 5 to 6 minutes. So let's try to continue working with this. We also learned how to calculate limit at infinity, right? So let me give you a couple of examples for limit at infinity. This is now 6. Let's say limit x approaches to infinity of 2x squared plus 3 over 4x squared plus 5x plus 6. By now it should be clear that I am writing this expression, this functions randomly, right? You can create your own example. I showed you 3 methods, right? Out of them, let me use the second method. As I said, the one that is very popular. Eliminate the tail of the top polynomial. Eliminate the tail of the bottom polynomial. And put limit symbol in the front, right? You can cross out x squared from the top and the bottom. looks like I end up getting 2 over 4, it's just 1 by 2. Variable x is gone. This is the limit of the given function. So computing limit at infinity, not a big deal. If you want to use the degree result, that's fine too. Degree of the polynomial in the top is 2, degree of the polynomial in the bottom is 2. Since the degree is same, ratio of the leading coefficient is limit at infinity. And that is also same as the horizontal asymptote for the function. All right. Finally, let me show you one example of continuity in terms of graph. All right. So let's say I give you a graph of some function. Suppose this is how the graph of some function look like. Let's say the function has a hole in one point. It has a vertical asymptote somewhere here. Let's say it also has a jump and maybe a sharp corner. All right. There are 4 interesting inputs. Let me label those inputs. P, Q, R, and S. These are 4 different inputs where something weird occurs with your function. This is the input where function has a hole. This is the input where your function has a vertical asymptote. This is the input where the function has a jump. This is the input where there is a sharp corner. Let me give you the value of each one of this, right? So maybe this value, let's say this is W1, this value, this is W2, and this value, let's label it as W3. Okay, I'm going to ask the following questions. I'll create a table with 3 columns. All right, I will put value x equal to a in here. The first question will say, is f of a defined? If yes, give the value. Second portion will say, does the limit x approaches to a f of x exist? If yes, give the value. And then finally, is f of x continuous? Remember, if prediction match with the exact value of the function, that's when we can say the function is continuous. There are 4 inputs here, P, Q, R, and S. Let's fill out the information. All right. At input P, what's the exact value of the function? Well, looks like there is a hole there. So we don't know the exact value. Function is not defined at input P. So I would just say undefined. Does the limit exist? Well, think about it. If you go close to P from the left side or right side without touching P, looks like this is going to go closer and closer to W2. All right. Estimation says that we are going to get closer and closer to W2. Is your function attaining value W2 at P? Answer is no. Right? So function is undefined, but limit exists. They are not equal, so this is not continuous. Okay. Let's look at Q. What's the exact value of the function at Q? Looks like it's a vertical asymptote. Really the bad input for the function. Value is undefined. What's the limit? If you go close to Q from the left side, it will take you to negative infinity. This will take you to positive infinity. So limit D and E, it's a vertical asymptote. They are not equal. Function is not continuous. For R, there is a jump. What's the exact value of the function? Look at that solid dot. Let's label this as W4. Okay. The exact value of the function is W4, represented by that solid dot. Does the limit exist? Well, if you go close to R from the left side, looks like you are reaching at W2. If you go close to R from the right side, you are going to reach closer and closer to W4. All right. So meaning limit does not exist because left and right side prediction don't agree. This is not continuous. What about the last input at S? At input S, exact value of the function is W3. All right. What's the limit prediction? If you go close to S from left or right side, looks like the function is getting closer and closer to W3. Look, limit prediction match with the exact value. Function is continuous. By looking at it, you can say right away, graph is not breaking, so function is continuous. All right, so looks like we already are running out of time. So I don't, or maybe let me give you one problem for checking continuity as well. Won't take more than 1 or 2 minutes. Uh, Three questions you would like to ask, and I'm going to keep this picture right here so that uh, you can check it. Let's say I give you this function f of x equal to x square minus x square plus x minus 6 over x square minus 9. Should look familiar to you. We have used this function recently. All right, minus 4, I guess, right? Here is the set of question. Is f of 2 defined? Number 2, does f of x, does limit x approaches to 2 of f of x exist? If yes, value. And then number 3, is f of x continuous at x equal to 2? All right. It's a perfect example. You will be able to relate it with this particular focus on that whole part. Okay. Uh, Put x equal to b in your x equal to 2 in your function. 2 square plus 2 minus 6 over 2 square minus 4. Look at that. This is 6 minus 6, 4 minus 4. This is 0 over 0, meaning f at 2 is undefined. Look, at whole, the value is undefined. Okay. Does the limit exist? Let's calculate. We already know how to handle indeterminate form, right? So I'm going to use factorization technique. Factorize the top polynomial x plus 3, x minus 2, bottom polynomial x minus 2, x plus 2. Cross out that location of the whole and then apply the limit x approaching to 2, x plus 3 over x plus 2. If you apply the limit, you end up getting 5 over 4. All right, limit exists, it is 5 over 4. So prediction tells me that there should be some value. Exact value of the function is unknown, so function is not continuous because the limit prediction does not match with the exact value of the function at 2. All right. So
Professor,
yes. All right. So let's stop here. This is a good point to stop. Now I can take any questions that you may